In this presentation, I'll be explaining three-phase alternating current system or three-phase AC system. Now let us see the concept of three-phase alternating current generation, three-phase AC generation. Now this pictorially, this system is represented as a three coils. They are kept in between two magnets or magnetic, that north pole and south pole. There's a uniform magnetic field is there in between this north pole and south pole, and there are three coils. Red, that is represented as red coil, that is R phase, and this is Y phase, Y1 and Y2. This is R1, R2, Y1, Y2, and the third phase is B1, B2, B phase. There are three coils are there that is rotated in the magnetic field, in the constant magnetic field that is rotated. Now consider, let us see the one coil that is first, that is R phase. Let us see the R phase here. When R phase is rotated, now the basic principle of operation is the Faraday's law of magnetism. That is, Faraday's law of magnetism means that when a coil is rotating in a uniform magnetic field, a voltage will be inducing in the coil, and the voltage induced is proportional to the rate of change of flux linkage. Now, if this particular coil, that is the R1 and R2, that's the two ends of the coils, can say that starting of the coil R1 and finishing of the coil R2, that is rotated in a uniform magnetic field. And when this is like this one, when it is parallel to the magnetic field, that is corresponding to minimum flux. The minimum flux will be cutting when it is parallel to the uniform magnetic field. When the coil is vertical, there will be maximum flux will be cutting. That is, when the coil is coming perpendicular, the maximum flux will be cutting. This one. And as the coil rotates, the amount of flux that is cutting will be different. Basically, it is a cosine of that angle. That is, if you measure the angle from this one, what is the cosine of that one will be cutting that one. Now, the voltage induced in the coil is proportional to, as per the Faraday's law of electromagnetism, the voltage induced in the coil is proportional to the rate of change of flux linkage. And here, if, for example, if the coil is coming vertical to this one, vertical to the magnetic field, the flux will be maximum, but rate of flux linkage will be minimum, or that is equal to 0 here. And if the coil is, say, in parallel to the magnetic field, flux will be minimum, but rate of change of flux, or that will be maximum. Therefore, when the coil is vertical, that one, you will be, voltage induced will become 0, and when it is parallel to that one, the voltage induced will become maximum. Therefore, the same thing is explained in this diagram. You can see that one. Once the coil is here vertical, that is vertical to the electromagnetic flux lines, then there the voltage induced in the coil equal to 0. Now, as the coil rotates, and that is making an angle here, for example, here it is making an angle with the magnetic field 60 degree, then the voltage induced will be, of course, that is equal to sine 60 of that maximum value. And again, if the coil is rotated and that reaches to the parallel to the magnetic field, flux is minimum, but rate of change of flux is maximum. Therefore, that is why maximum voltage will be induced here. Therefore, this corresponds to the case when the coil is parallel to the magnetic field. Therefore, that will be continuing that one. Therefore, in this coil, as the coil rotates from here, if you say vertical case 0, then increasing and then reaching to maximum, then it will be again 0, then again reaches to the minus maximum, or the voltage induced in the coil, in a single coil, if you see that one, the voltage induced will become sinusoidal. Therefore, now we can consider three phases. The first phase R phase, second phase equal to Y phase, and third phase equal to the blue phase. It is rotated like that one. And the second phase Y phase is 120 degree lagging with the R phase. And again, B phase is again lagging 120 degree with respect to the Y phase. Therefore, if you plot the corresponding waveforms here, the corresponding to the red phase, this is the sinusoidal voltage is, as I already explained, a sinusoidal voltage is induced in the coil R1 and R2 after completing one rotation. Now the second phase, that is Y phase, is lagging the red phase by 120 degree. Therefore, this is the red phase that is lagging the, sorry, that is the yellow is the yellow, the second phase that is lagging the red phase by 120 degree. Therefore, that is the, again, that is producing its sinusoidal voltage, but of course that is lagging the red phase by 120 degree. The third phase, blue phase, that is B1 and B2 are the ends of the winding, and the voltage in that one, again, that is lagging the phase, yellow phase, again by 120 degree. Therefore, the B phase is lagging the yellow phase again by 120 degree, and same voltage is induced, sinusoidal voltage is induced like that. Therefore, when the three windings R1, R2, B1, B2 and C1, C2, they are separated by 120 degree, when it is made to rotate in a uniform magnetic field, three phase voltages are generated, that is red phase, Y phase and B phase. Three sinusoidal phase voltages are being generated. And the corresponding equations are, for example, in the case of red phase, if you say Vm sin omega t, R equal to Vm sin omega t. Second phase, Y equal to, of course, Vy equal to Vm sin omega t minus 120. It is lagging the red voltage, the voltage in the red phase by 120 degree. Vy equal to Vm sin omega t minus 120. And the third blue phase, it is equal to Vm sin omega t minus 240. Therefore, these are the equations of the three phase voltages, and the three identical coils are placed at 120 degree between each other, and they rotate in a uniform magnetic field. And as per the Faraday's law of electromagnetic induction, a voltage are induced, and the voltages are, equations of the voltages are like this one. And the sinusoidal voltage is generated across each coil R1, R2, Y1, Y2, and B1, B2, and they are placed at an angle 1. Each coils are placed at 120 degree. Therefore, a three-phase voltage, each one displaced by 120 degree, is being generated here. Yes, it is vectorially shown here. Phase of diagram, it is shown here. This is the R phase, and this is the Y phase, and this is the B phase. Each one is displaced by 120 degree. Therefore, this is rotating at what's the frequency that decides the frequency. Therefore, that is rotating at angular frequency. Therefore, this is a phasor diagram, and these are the equations of the three phase generating voltages of each phases: R phase, Y phase, and B phase. Now, in order to get an idea of the rotating phasor and sinusoidal waveform that's represented here, as we have seen that, as I told you, the flux in the phasor, the phasor is rotating at angular frequency. The first, when it is equal to 0, that this is the corresponding voltage. When it is rotating to 30 degree, this is the voltage. And when it is again rotating by, again, say 60 degree, the corresponding voltage is 1. And when the vector is rotating to 90 degree, the corresponding voltage is equal to maximum voltage you'll be getting. Again, that is repeating, and corresponding to 180 degree rotation of the phasor, it will be again 0 voltage getting. Then it is rotating again, that once it reaches to 270, there will be minus maximum voltage, minus AM comes here. Again, that is coming to the 0. Therefore, after complete, once the phasor rotating through 360 degree, the voltage is changing in a sinusoidal fashion like this one. This corresponds to 0 degree, 180 degree, and 360 degree. This is for a single phasor or single vector, and the same thing for the three phase. Therefore, that is represented as a three phase vector diagram, as I already explained the last slide. This is the R phase corresponding, and this is the Y phase, which is 120 degree lagging and again 120 degree lag in B phase. Therefore, that is rotating at the angular frequency. Therefore, three phase voltage will be generated. Therefore, this is just to explain that as the phasor rotating here, the corresponding variation in voltage is indicated here. Therefore, this is a sinusoidal waveform in time domain, and this is a rotating phasor. Now let us see what is meant by the three-phase generation, that is phase sequence, continuing the phase sequence of that one. Phase sequence means here it is the sequence or order in which the voltage in the three phases reach their maximum value. For example, in a three-phase voltage, as we already explained here, this is the R phase and the yellow phase, and this is the blue phase. Therefore, that is reaching the maximum magnitude. You can say that when first R will be reaching to maximum. After 120 degree, Y will be reaching to maximum. Again, after 120 degree, B will be reaching maximum. Again, that will be repeating. Therefore, the phase sequence of this one is equal to RYB. First R, then Y, then B, then again R, like that will be continuing. For the phase sequence is the sequence or order in which the voltage in the three phases reaches to their maximum magnitude. The same in phasor diagram. This is the R phase. Since this is rotating in the anti-clockwise direction, therefore this is the R phase. After 120 degree, this will be coming, and again after 120 degree, B will be coming here. Therefore, the phase sequence is that R, then Y, and then B. Or the phase sequence is RYB. Now let us see the advantages of three-phase system as such. First one is that power to weight ratio of a three-phase alternator is high as compared to single-phase alternator. That is the first advantage of three-phase. Or the meaning is that for the generation of the same power, the size of three-phase alternator is less compared to the size of single-phase alternator. Because to generate the same power, the size is less in the case of three-phase alternator. Or that is why that's the first advantage of a three-phase system. And another way of explaining the same thing is that for generation of the same power, of course, the cost, weight, volume, etc. of a three-phase generator is less compared to the single-phase generator. Therefore, that's the first advantage of a three-phase system in which the power to weight ratio of the three-phase alternator is high. As three-phase system is high as compared to the single-phase alternator. That is, power output for a very small weight, you're getting maximum power output. Therefore, the three-phase voltage has been shown here. This is the single-phase voltage. Now, continuing the advantages, single-phase motors are not self-starting, but three-phase motors are self-starting. Therefore, we have to provide separate starting, element as a capacitor is to be added in the winding. Therefore, in order to produce, because here in a single-phase motor, that's only a pulsating torque, pulsating magnetic field is there. But here in a three-phase motor, there is a rotating magnetic field is there that will be producing the torque. Therefore, in order to produce the starting torque, we have to provide a capacitor is to be connected in the case of a single-phase motors. That is why single-phase motors are not self-starting, but three-phase motors are self-starting. It's an advantage of three-phase system. Another advantage is that for electric power transmission and distribution of the same amount of power, the conductor material requirement is less in three-phase compared to the single-phase. Compared to the single-phase, the amount of material used is to transmit the same power. The amount of material used is less in the case of a three-phase system. Another advantage is that parallel operation of a single-phase alternator is not very smooth, but but in the case of three-phase alternator, it can be easily connected in parallel operation is possible. So these are the under advantages of a three-phase system. Now let us see the different connection of a three-phase system or three-phase connections. Mainly there are two types of interconnection in a three-phase system. One we call it as star connection or Y or star connection like this, or delta connection or mesh connection. There are two types of connection, and this is called the star connection. You can say that three windings R1, R2, B1, B2, Y1, Y2. These are connected in a star, and star in the sense here, just to remember, the similar ends are joined here. That is the starting and the finishing of R phase, starting, finishing of the B phase, starting and finishing of the Y phase. Therefore, all these are joined together. Similar ends are joined together. That is why just to remember the star, in a star connection, similar ends of the windings are joined together. Here, R2, B2 and Y2, they are joined together. And here, this is a phase R and this is the phase B and this is the phase Y. Therefore, these are the three R, Y, B phases, and other element in the finishing ends of that one, R2, B2 and Y2, they are joined together. Similar ends are joined together, and that point can be connected, or that line can be taken as a neutral wire. Therefore, this is called the neutral point, and this is the R phase, R line, and this is the B line, and this is the Y line. Of this method of connection, we call it as star connection. Therefore, in star connection, similar ends of the windings are joined together. Therefore, in this case, R2, Y2, B2, they are joined together here. This is a star connection. In delta connection, the dissimilar ends of the windings are joined. Dissimilar ends in here, as an example here, R1 and B2 are joined here. The dissimilar starting of the R winding and finishing of the B winding. Therefore, R1 and B2 are joined, R2 and Y1 are joined, and B1 and Y2 are joined. Dissimilar ends are joined together. And this method of connection, we call it as delta type of connection. And again, this is the R phase, and there is the, of course, the R phase, Y phase, and this is the B phase. But in delta type of connection, there is no neutral conductor. There's no neutral conductor, and the dissimilar ends are joined together, and it's like a R1 and B2 are joined, Y1 and R2 are joined, and B1 and Y2 are joined. Dissimilar ends are joined together in a delta type of connection, and similar ends are joined in the case of star connection. But in star connection, there is one more terminal is available, that's called the neutral wire, but that is absent in the case of a delta type of connection. Now let us see the star connection or Y connection. Here, this is a star connection, R1, R2, Y1, Y2. This is B1, B2. Therefore, R2, B2, Y2, they are joined together. And this is the neutral conductor. This is the R phase, and this is the, of course, the Y phase, and this is the B phase. And there are voltages. There are one we call it as, there are two voltages is there. One we call it as phase voltage, and phase voltage is the voltage of the phase with respect to the neutral, or it is a voltage between the phase and neutral, that we call it as phase voltage. As an example here, if you see this one, see this is what is here. Here VBN, the voltage of the B phase with respect to the neutral, that's the phase voltage. Similarly, this is the VYN, and this is equal to VRN. For the voltage of each phase with respect to the neutral point, or the phase voltage between the phase and neutral, that is called as a phase voltage. Between phase and neutral, it's called the phase voltage. And the voltage between each phases, that's called the line voltage. That is, we can say that phase R and phase Y, it's called the VRY. That's a line voltage. Similarly, the phase Y and phase B is equal to VYB. It's a line voltage. And here R and B, VRB is also line voltage. Therefore, the line voltages are the voltage, that is the voltage between the phases or lines. That is VRY, VYB, and VPR. These are called the line voltages. VRN, VYN, and VPN, these are called the line voltage, and these are called the phase voltages. Now, they are vectorially related. We'll be seeing in the next slide the derivation of etc. And yes, it is shown here. This is equal to, say, as an example here, this is equal to VR. Just shown as one. This is equal to VR, and this is equal to VY, and this is equal to VB. VR. These are the VR, VY, VP is same as VRN, VYN, and VPN. The phase voltage. Red phase with respect to the neutral, Y phase with respect to the neutral, B phase with respect to neutral. Therefore, these are the phase voltages. From this phase voltage, you can calculate what is the line voltage. For example, in order to calculate VRY, this is a VR, and VRY equal to VRN minus VYN. VRN minus VYN. Therefore, this is VRN or VR, and this is equal to minus VI is this one. If you vectorially add as a parallelogram law, if you add these two vectors, VR and for the minus VI, then this vector represents the line voltages VRY. Same as that one, you can calculate what is the VYB, and this is equal to VBR. Therefore, these voltages are called line voltages, and these voltages are called phase voltages. Phase voltage is the voltage between a phase and neutral, and the line voltages are the voltages between two lines. Therefore, VR, VN, VB, that is represented in this one, that is same as VRN, VYN, and VPN. Then we can derive what is the relation between line voltage and phase voltage of a star connected system. Now coming to the star connection, as a continuation of the derivation of the line voltage. For the phase voltages, as I already told you, VRN, VYN, VPN, that is the voltage between phase R and neutral, phase between Y and neutral. These are called the phase voltages, and that is represented as here VR, that is represented as VR, VY, and VB. For VR, VY, VB are the phase voltages. That is same as VRN, VYN and VBN. And the line voltages are VRY, VYB and VBR. That's called the voltage between the two phases. In order to derive that line voltages in terms of the phase voltages, that is, for example, VY, this is a VRY, VR minus VY. VR is this vector, Vy is that, minus Vy is this one, projected in the 180 degree. Therefore, if you add these two vectors, you will be getting what is Vry. Therefore, in order to add as per the parallelogram law, this vector, that is Vry, this is equal to the vector magnitude equal to root of Vr square plus Vy square plus 2Vr Vy cosine of this angle, cosine of the angle between Vr and minus Vi, this angle equal to 60 degree. Therefore, here VR, Vy, that is, I can represent it as V phase, because VR, Vy and Vb all are the phase voltages V phase. Therefore, I am substituting this one VR, Vy and cos theta 60 degree here, theta equals 60. Vry equal to root of V phi square plus again V phi square, both are equal magnitude, plus 2 V phi into cos 60. Again cos 60 equal to 1 by 2. If you substitute that one, we'll be getting root 3 V phi's, or line voltage equal to, this line voltage Vry equal to root 3 times the phase voltage. Therefore, in a star connected system, the line voltage equal to root 3 times phase voltage. Same other phase also. And here the same thing can explain. This is the line voltage which is equal to Vyb, and this is equal to Vbr. Therefore, each one is equal to root 3 times the magnitude of the line voltage is equal to root 3 times the phase voltage. Therefore, in a balanced, all phases are equal. In a balanced case, that's called all phases are equal and they are displaced by 120 degree. In that case, three-phase star connection, line voltage equal to root 3 times phase voltages. As an example, if the phase voltage equal to 230 volt, line voltage equal to root 3 times 230, almost equal to 400 volts. Therefore, this is a relation of the line voltage and phase voltage. Line voltage is the voltage between the two lines, and phase voltage is the voltage between line and neutral. Now let us the power in a star connected load here. Again, star connected current, in star connected case, line current is same as the phase current. You can say that one, the current through the line equal to line current. Phase current is the current flowing through the phase. Therefore, line current equal to phase current, and line voltage equal to, as we already seen, root 3 times V phi. These are the relation for a star connected system. And power in a three-phase star connected system, 3 times power consumed per phase. The 3 times for 3 phases are there. The power in consumed in each phase into 3, or 3 into V phase into I phase into cos phi, where cos phi is the power factor of each phase. Therefore, phi is the phase angle between phase voltage and phase current. Therefore, but we have already seen that phase voltage equal to line voltage divided by root 3. This is a relation, and phase current equal to line current. Now, if you substitute in this equation V phase and I phase in this equation 1, you'll be getting 3 times V line divided by root 3 into I line into cos phi, or root 3 VL IL cos phi. This is called the active power. Active power is equal to, that's what we have derived here, P equal to root 3 VL IL cos phi. Therefore, in a star connected or even delta connector, same equation is same. Here, the power is equal to root 3 VL IL cos phi. VL is the line voltage, IL is the line current, cos phi is the power factor. And here, in star connect case, line current is same as the phase current, but line voltage equal to root 3 times phase voltage. That is the active power. And reactive power, it can be calculated root 3 VL IL sin phi. And apparent power and active power and reactive power, they are as a represented by the power triangle. This is the active power, this is the reactive power, this is apparent power, or apparent power equal to root of real or active power square plus reactive power square, that is equal to apparent power, or SC equal to root of P square plus Q square, which is equal to root 3 V into VL into IL. Root 3 into VL into IL is the apparent power, root 3 VL IL cos phi is the active power, root 3 VL IL sin phi is the reactive power. Okay, star connected load. Now, to calculate neutral current in a star connected circuit, therefore there's a neutral wire is there. It's a 3-phase 4-wire system in which this is the neutral conductor, and this is the R phase, this is the Y phase and B phase, and you have to calculate the current that is flowing to the neutral. Neutral current equal to, as per the Kirchhoff's current law, there's a current coming here, and here it is equal to IN equal to IR plus IY plus IB. As per Kirchhoff's current law, you are applying KCL to this point. IR plus IY plus IB equal to IN, neutral current. Now, it is IR equal to IR sin omega t. Of course, the second phase IR sin omega t minus 120. Again, current equal to IN sin omega t minus 240. Now, if you substitute this one in this equation, neutral current can be calculated IM sin omega t plus IM sin omega t minus 120 plus IM sin omega t minus 240. Now, if you expand this one, you can get it as it is equal to Im sin omega t minus half Im sin omega t, again minus half Im sin omega t equal to 0. Or meaning that if the load is equal and if it is balanced, that is phase voltages are equal, if the phase impedance are same, it's called balanced condition. Under balanced condition, the neutral current equal to 0. In a star connected system, the neutral current equals 0. In a balanced case, that is phase voltages are and phase impedance are equal in magnitude, then three-phase wire system neutral current equal to 0. That is why this is the equation to the neutral current calculation method, and here neutral current equals 0 under balanced condition, three-phase balanced star connected system. Now coming to the delta connection system, as I told you, delta connection system, the dissimilar ends are joined together. That is R1 is connected to B2 and R2 is connected to Y1 and B1 is connected to Y2. Therefore, this is called a delta type of connection. In this one, here there's no neutral conductor. This is R phase, this is Y phase, and this is a B phase. And these are called the phase currents. In a delta connection, phase current that is flowing IBR. Then here IYR and IRY. These are called the phase current. That is the current flowing through each phase is called phase current. And these are called the line currents. This IR, IY, and IB. These are called the line currents. Now, in a delta connection, we can see that one. These are called the line voltages, and this again the voltage across the phase equal to the phase voltage. Line voltage equal to the phase voltage. Therefore, in a delta connection, the voltage between each phase is same as the voltage between each lines. Therefore, the line voltage is same as the phase voltage in the case of a delta connection, but line current is different. Line current is not same as the phase current. To calculate, that is why to calculate IR, if you see that one current IR equal to IRY as per the Kirchhoff's current law, you can calculate IRY minus IBR. IRY minus IBR equal to the line current flowing this one. Again, IY equal to IYB minus IBY. IB equal to IBR minus IYB. Therefore, the line voltage in this case, the line voltages and are VRY, VYB, and VBR voltage between two phases. That is same as the line voltages, but the currents are. The line current is not same as the phase current. You can calculate this line current again as this one. Again, you have to calculate what is IR. IR equal to IRY minus IBR. Therefore, here, if you plot, that is the phase currents as a three-phase phase current here. The three-phase phase currents have been shown here. Here, IRY, IBR, etc. These three-phase currents are shown. And in order to calculate IR equal to IRY minus IBR, IRY minus IBR, and that is added here. This is the line current, same as we are showing the line voltage in the case of a star connected system. Therefore, in a delta connected system, line voltage is same as the phase voltage, but line current will be deriving that is equal to √3 times phase current. Therefore, in delta connection, magnitude of the line voltages are same as the phase voltage. Magnitude of VL is same as magnitude of B phase. Continuing the delta connection, here this is the same delta connection shown. As I told you, IR equal to IRY minus IBR, IY equal to IYR minus IRY, IB equal to IBR minus IYB. Therefore, that each current, for example, IR equal to this one equal to this one minus this current. Similarly, you can apply the Kirchhoff's current law to these nodes here, and you can calculate. Can derive the equation. These are the line currents IR, IY, and IB. And the phase currents are IRY, IYB, and IBR are displaced by 120 degree. Therefore, these phase currents are displaced by 120 degree. And in order to calculate IR, IY, and IB, that's called the line current. Therefore, here, in order to calculate that one, we have to see the vector diagram of this one. Coming to the three-phase vector diagram of the phase currents, this is the phase current IRY. Again, this is displaced by IYB is displaced by 120 degree. Again, this is IBR is displaced by 120 degree. Therefore, these are the phase currents. Now, in order to calculate the line current IR, which is equal to IRY minus IBR. Therefore, IRY minus IBR. Minus IBR means this is projected in this direction, opposite direction, 180 degree shifted. Therefore, vectorial sum of these two will give the what is the line current IR. And the angle between them is equal to again 60 degree. This angle equal to 6. This is 30. So the total angle between this IRY and minus IBR, that is equal to 60 degree. Therefore, as per the previous equation that we already seen, same thing, parallelogram rule. Here this current equal to this square plus this square root of IRY square plus IBR square plus 2 IRY and IBR into cos 60. The angle between this is equal to 60 degree. Now, if you substitute this one as phase currents, IRY, IBR and IRY, these are called phase current. All are equal. Magnitude of the phase currents are equal in balanced case. Therefore, square root of I phase square plus 2 I phase into cos 60, root 3 I phase. Or in a delta type of connection, the line current equal to root 3 times phase current. Root 3 times phase current. Or in delta connection, line current equal to root 3 times phase current and line voltage equal to phase voltage. Or VL equal to V phase and IL equal to root 3 times I phase in the case of a delta connection. Now let us see the power in a delta connection. Same circuit, delta type connection. DC elements are joined together. R1, R2, B1, B2. B1, B2, the R1 and B2 are joined. Again, this is called a delta type of connection. And these are IR, IY, IB, these are called the line currents. And these are the current flowing through the phases, that is called the phase currents. And we have derived the relation between the line current and phase current. Line current equal to root 3 times phase current and line voltage equal to phase voltage. In a balanced load condition, impedance and power factor of the load in each phase is same. That's called the balanced condition. Impedance will be same, voltage will be same, as well as phase between each one, all are 120 degree apart. That's the balanced case. With balanced load condition, magnitude of the current flows in each phase are same. Therefore, the current flowing through this each phase are same. Similarly, line current magnitudes also same. Now, coming to the derivation here, let I phase be the phase current and IL be the line. I phase is the phase current, IL be the line current. V phase be the phase voltage. The power per phase is, as you know, that one V phase I phase into 3 cos phase. Therefore, the total power consumed by each one, that the power per phase is equal to V phi I phi into cos phi. The total power consumed by the 3 phases equal to 3 times V phase I phase into cos phi. But in delta connection, we have derived that one V phase equal to V line, or line voltage is same as the phase voltage. Therefore, VL equal to V phase and IL equal to root 3 times I phase. Substituting this one here, we'll be getting substituting here 3 into VL into IL by root 3 into cos phi, or root 3 VL IL cos phi. And again, the active power equation is equal to root 3 VL IL cos phi. Of course, the reactive power equal to root 3 VL IL sin phi, and the apparent power equal to root 3 VL into IL, same as in the case of a star connected load. Therefore, this is the equation for the active power, root 3 VL IL cos phi, where VL is the line voltage, which is same as the phase voltage in delta connection, and IL is the line current, which is equal to root 3 times the phase current. Phase current means the current that is flowing through the phase. Line current is this current. That current is root 3 times the phase current in the case of a delta connection. And in star connection, the difference is that line voltage equal to root 3 times phase voltage, and both line current and phase currents are equal. Therefore, that's the difference between star connection and delta connection. In each cases, the active power consumed by the load is equal to root 3 VL IL cos phi.